is saving the day as usual. Okay.
I'm just closing the other file.
I'll make this really brief. Let's, there are many things we could say about Professor Elitzur, as we affectionately know him. Maybe what you don't know is he quit high school early, joined a lab, and then found Yakir, then at Tel Aviv University, and did his PhD with Yakir in the olden days. And since then, he's become a enlightening figure in the foundations of quantum mechanics and also philosophy of mind, and so many things that Avi has done there. So please join me in welcoming Professor Elitzur.
Thank you very much. Don't need a mic or anything like that.
No, it picks it up very well.
Very good. It's an honor to be here, and actually it's a double celebration. We are celebrating Yakir's birthday, and we are celebrating the opening of this Institute for Quantum Studies. So for this reason, I won't talk about quantum mechanics today. I'm going to talk about life and death. We are all physicists. Most of you here are physicists, and you know that there is a great difference, major difference between physics and biology, at least the kind of theoretical physics that you're doing. The physicist usually tries to make things as simple as possible. Give me one particle, give me a very clean situation, making things if you want to go to the foundations. In biology, it never works like that. You can't make generalizations about life without studying endocrinology, biochemistry, physiology, and so on. So there is always a kind of tension between the two disciplines. This is best illustrated in the tragic case of two scientists who were sentenced to death. And the day that they were about to be executed, they've been asked what is their last wish. So the physicists say, for many years, I have a theory of biology which explains life. I would like to give here a seminar before you guys kill me. And they said, fine. And then they asked the biologist, what's your last wish? And he said, I'd like to be executed before my colleague begins his talk. So I'm a physicist, but I'm interested in questions of life and death and so on. And I think that thermodynamics gives us a very fresh look to do what biologists usually loathe, to say interesting things about living systems, about organic life, without always knowing all the details that even the biologists may find interesting. I'll be very brief because this should be a popular talk, so no mathematics, but this is a sound model with calculations and so on. So just as a reminder, why do we think that thermodynamics is the best approach for the physicist to understand the beautiful thing called life? Thermodynamics studies energy and entropy transformation, and this is what is so beautiful about thermodynamics. The laws of thermodynamics are valid regardless of the system's chemical composition or the kind of energy it produces. So even if you ever find an alien and you don't know what they are made of or what kind of energy drives them, you can be sure that they will emit some infrared radiation. So general is so ubiquitous is thermodynamics that you don't have to know anything about its details. Or when you go to the patent office and say, I have a perpetuum mobile, and you're a distinguished professor of physics, and you show all the details, the guy there says, look, I don't know anything about what you are talking. If you are violating the first or second or third law of thermodynamics, out, and they don't even bother to check it. And you may say, why? Because the laws of thermodynamics are ubiquitous. So this is a good approach to understand the plethora of life, plants, animals, mushrooms, and so on. So its jurisdiction is therefore ubiquitous. Thermodynamics has a measure of entropy or order, which is good for understanding information and complexity, to other hallmarks of life. So this is another reason to use thermodynamics. So there are 4 laws of thermodynamics, which we don't have to go into. First law, which energy is conserved. Second, which is going to interest us most, the entropy of an isolated system can only go up. Then there is a third law. What's the next law? If there are 4. 4 laws.
0.
Right, Jeff. The zeroth law, and no need to go into that. We are interested in the second law, which says that entropy always goes up. So without mathematics, just a visual illustration. Here I have gas in one side of the box with a partition. I make a hole, and after a while, I have the gas evenly spread. So I say entropy was low, now higher, and now it is maximal. I can also do the same thing with the energy, that is having the hot gas and cold gas on one side, and there will be equilibrium in terms of energy. It's the same. It's important to know that because sometimes college professors will ask you when some material crystallizes, isn't that showing you that that order usually goes up? And then the students can say, yeah, entropy goes down in terms of the chemical, of the matter, but not in terms of the energy, because the new crystal produces heat, just as an exercise. So it goes from order to disorder, either in matter or in energy. So entropy, and that's another interesting thing, entropy usually involves a degradation of energy's efficiency. Nowadays, I'm old enough to remember using chalks or markers in the high school at the lecture room. So we don't have it now, but imagine that I had a marker here and I would roll, oh, what do you know? I have a chalk. So if I roll it, I can see that after a while it slows down and stops. And then you ask the students what happened to the energy. There was kinetic energy and it's gone. And then they tell you that it turned into heat energy, zillions of small molecular motions that you can see them. It took me many years to realize that actually I am doing just the opposite with the muscle that moves the chalk, because many molecules of actin and myosin, which are microscopic, converge to one motion which moves the chalk. So that's a very interesting way to look at the difference between entropy increase in inanimate matter and decrease in animate matter. So usually we have all kinds of energy, mechanical, which does work, and so on. All of them degrade to heat eventually. We never see, with the exception of life, sometimes heat, which is the least efficient kind of energy, just going up, being upgraded to mechanical or electric energy. Think about a lizard's egg. So all you have there, it uses heat from the surrounding, plus the chemical energy that it has. But eventually what you get there, and there is no energy gradient, there is no heat gradient like in birds and so on, and still you get energy going up, being upgraded in terms of efficiency. This is something that engineers usually love most. So that's the second law, and just once again a reminder, you can lower entropy. Suppose I dispersed all these billiard balls, so I can actually lower them here in Chapman. If Andrew wishes to do it in his laboratory, then he can take many technicians, arrange it, all the balls come back and eject back one ball, such that all the energy is now in one ball. However, then comes the dean and says, what happened in the Institute of Quantum Studies? There was a lot of entropy going on there. So Andrew can go to Daniele, who is still president, and convince him that Chapman, all of Chapman would now help to reduce the entropy produced by this small institute. And they'll do it. Who is the mayor of Anaheim, or I don't know. Eventually it will go to the White House, and you will see that always when you lower entropy in a small place, entropy will increase more outside, such that always entropy of any closed system, and eventually the universe goes up. Thou shalt not lower entropy. This is Loschmidt's paradox, which is very beautiful. A guy named Loschmidt asked Boltzmann, if this is the state of a system, entropy is not maximal and not minimal. Boltzmann believed that just by mathematics he can derive the arrow of time. So what do you think is going to be the future of this system? And poor Boltzmann said, of course, there is going to be more entropy. Then he asked him, what is going to be the past of this? of this system, and he said less entropy. He said that you can do that by mathematics. You don't have T or minus T in your equation, so you're assuming that there is a difference between past and future, but actually there is not, and you could not explain it. So this is Ludwig Boltzmann, who died in 1906 by suicide. That was his very gifted student, also died for the same reason. And that was Julius Robert Mayer, who survived the suicide attempt much earlier. So please don't take seriously what I'm saying here. It's just thermodynamics, and you can always ask me if there are questions, and there are still many.
Don't study thermodynamics.
Ibrahim is wise. He says, yeah, go to quantum mechanics. Thank you, Ibrahim. So I'm going to offer a kind of crash course measures of entropy. Entropy is disorder, and for anything that I'll say here, you can be sure that there will be some professors here on campus which will say this is absolute nonsense. This is not the way to teach students thermodynamics. Each of them has their own favorite measure or definition. My approach is inclusive. Bring them all, and I'll show them. And I love to show you that they're all consistent. So you look at an adolescent's board, and you say this is ordered, this is not disordered. Randomness. So if your adolescent child just comes, takes clothes and so on, you will never see things just going by themselves to be ordered. It goes from disordered to ordered. I'll talk later about the difference, which is very important, between order, random, and complex, which is different. Complexity is different from order. That will come later. Equilibrium. So you remember, equilibrium means that high entropy, you can also measure it by the degree of equilibrium. And you can see that this board, this closet of a child, of an adolescent child, is far from equilibrium. You have the same chance of finding trousers in every compartment, whereas in order to be ordered, it should be out of equilibrium. Number of compatible microstates. Again, there are numerous more ways to make a closet disordered than ordered. I mentioned earlier irreversibility. Again, the same. It goes usually one way rather than the other. Dissipation of heat. Can talk about it later. And decrease of energy's efficiency. Now, here's the interesting thing. So usually you will see hot compartment and cold compartment becoming lukewarm. You will never see them separating again, because then heat energy, thermal energy would turn into mechanical energy. This is all known to you and probably pretty boring. The interesting thing is that for any measure of entropy, I can find another hallmark of life, which is precisely that, but the opposite. We say that entropy means greater degree of disorder. Hallmarks of life is usually this rodent or any flower that you see in the garden is much more ordered or complex. I'll make the distinction later. Life is certainly not random, certainly far from equilibrium. There is more heat within my body than outside, more liquids here than outside, more systola in the systola, more pressure in the systola than the diastole. One day, there will be equilibrium. Ashes to ashes, dust to dust, but that is death. Being alive means being far from equilibrium. How do we do that? And as I mentioned, few microstates, you go to the doctor to do blood tests, and you see few green numbers within the healthy, many more in the disease, and much more when you drop dead. So you have fewer microstates. Let me give you another example. Take a few molecules from my thyroid, where they are now, and put them in another place in the body. I'll be a completely different organism, much more aggressive, or even I'll drop dead. Whereas if you change a few molecules here or in some rock, that wouldn't make a difference. So life means being in a small number of microstates. Yes, life is much more reversible than death. It is easier to kill than than to give birth. I believe King Solomon said something like that. Hot can go from cold to top. I mentioned it earlier. Life usually upgrades the efficiency of energy from heat to kinetic, mechanical, or electrical energy. How do we do that? So we know that there is a difference, and usually the textbooks say the common textbook answer is that living organisms are open systems. It's non-equilibrium thermodynamics. They are correct, but it's not enough. So usually the textbook says, why isn't the entropy in my body going up? And the reason is because you inhale, you breathe, you go to the bathroom, so you're an open system. This is correct, but absolutely inefficient, because chairs are open systems. They exchange energy with the surrounding. Rocks, blackboards, trash cans, these are all open systems, and they are not alive. What is the thing which is so unique to life? That has to take us to, so here's the idea. Suppose that I want to dive into the ocean, I need a watch which is resistant to water. So I buy a very expensive watch, and it serves me when I dive deep. I assume that the Japanese or Swiss guy who constructed it has a lot of information about the physical conditions prevailing deep in the sea. So here's a simple question. How much information is in a fish? What I want to do is to rephrase Darwin's evolutionary theory and say that the more adapted you are to a certain environment, the more information you have about that environment. Trivial, isn't it? In order to be adapted, you need to have more information. This is what I love most. This is the kind of orchid. And you can imagine that there are, in Israel, we have some bees which look just like these flowers. And imagine a male bee mounting on one of these flowers. It also secretes the same pheromone. So he's very happy that he has found a date. And after a while, he sees that she is cold and she is not moving. And then he goes to another female and say, I had a bad day today, she was cold and she was not moving, and then once again is not lucky, and that female is also not responsive. So I would say that this orchid has a lot of information about the bee, okay? So adaptations means information. And here is Schrödinger, who once said, and he was ridiculed at that time when he said that all living organisms feed on negative entropy. And people say there is no such a thing as negative entropy. It is Roger Penrose who defends him very beautifully when he says that actually this is what happens. Think about the energy coming to our planet and the energy leaving it. It's the same amount of energy, but energy which comes on Earth are fewer photons, which are more blue, which have shorter wavelength, and those which leave us are more photons, which are more red. So there is negative entropy going in and positive going out. You probably know this kind of terrariums, which are completely closed. So no matter goes in and out, but there are some plants with all the water that it needs, and some insects, even some small organisms, and you can keep it for many years. They reproduce and die, reproduce and die. So this is a whole ecological niche by itself. All the material is there. In principle, you could store all the energy there. Make it large enough, make all the walls reflective such that all light will be reflected back, and it will preserve all the matter and energy. All organisms would die within few days for the reason that matter and energy are conserved, entropy is not. So although all the energy is recycled there, its entropy will go up. All the radiation would be eventually would be infrared, and then they would die. So what we need is light coming from the sun, not for the energy. There is enough energy there. You need to take out energy and bring new energy, because through that energy you bring more negative entropy. So this is why I think, not only me, Penrose and probably others, that Schrödinger was right in his intuition.
You mean there's just more degrees of freedom in this case?
Right, that's another way to put it. You probably all know Maxwell's demon. It's a very good idea to teach it in classes in thermodynamics. So here you have this tiny guy who actually monitors the motion of molecules coming from one side to another. So this tiny demon, which is of molecular size lets fast molecules go from left to right, but then shuts the door when a small molecule tries to do that, so it bounces back, and vice versa for slow molecules trying to go the other way. In time, you will have hot gas on one side, cold gas on the other side, so you have reduced entropy. You can use it now to do work, and it can be shown that you did not disperse much energy in order to satisfy the second law. It took physics about 100 years to solve this problem. There have been interesting solutions which failed. Yeah, I recommend this book, Maxwell's Demon by Leff and Rex. These are the guys whom you and I, Jeff, met in San Diego some years ago. So this volume is a beautiful anthology of all papers on Maxwell's Demon, mathematics, computer science, biology, physics, philosophy, and so on. So these were attempts of exercising Lord Kelvin, the guy who embarrassed Darwin many years ago by a question in thermodynamics, wrote a textbook in which he said, in which he reformulated the second law of thermodynamics as follows: it is impossible, psic, by means of inanimate matter, psic, to derive heat from a hot body to a cold body. So Kelvin believed that life is exempt from the laws of physics, at least from the laws of thermodynamics. It's an interesting idea, but of course it's wrong. Kelvin opposed Darwin, and he believed that life is eternal in the universe, and the universe is eternal. Again, come another physicist, von Smoluchowski, and he said, perhaps so while Kelvin was a kind of vitalist, he believed that there is something unique to life which cannot be explained in terms of physics. There were attempts to go to mind and say that because it is intelligent, then the soul or the mind is exempt from the laws of physics. We are not happy with that. But then came the 20th century, Szilard and Brillouin, and introduced something, a new currency to physics, which is information. And they say the demon has to use information in order to know which molecule is fast and which is slow. And you can show that in order to get this information. So that's important. If you have complete equilibrium in this gas, that means that although there is a lot of light there, you're absolutely blind. You can't see anything because light comes from all sides. You need, just in order to make an engine, you need to have a gradient of energy in order to produce work. You need to have a gradient of light in order to see. So that demon would have to introduce another source of light to that highly illuminated environment. And lo and behold, it turns out by the calculation that this additional light will increase entropy. So it was, and then Bennett and Landauer made the correction that actually it goes to the erasure of information. We can go to that later. So we learned something interesting. Information costs energy. Any operation that you do with information costs you energy. When the telephone company charges you and it is itemized, although they rob you each time, but actually the rationale is correct. The more information you want to pass to your friend, then to your friends, then the more energy that we have to use and the more that you have to pay. But then if information costs energy, that means that once you have information, you can save energy. With information, you can do some work with less energy, provided you do it at the right time or place. These guys are opening the door. They're making considerable work, using a lot of energy. What they lack, this small thing, which has a lot of energy in it. So you use little force, little energy at the right time and at the right place. If you have been to India, you don't want to meet this guy on the left. Tiger would smash you in a minute, you know, such a strong, powerful machine, and you don't want to face them. But you don't want to face even this miserable guy who is very weak, extremely weak. And all it can do is just give you a spit into your eyes and then give you a small sting and a very little amount of molecules. This is should be neurotoxin. In this case, it is cobrotoxin, which is very similar to your acetylcholine. So that means that the cobra has a lot of information about your nervous system. So again, the cobra is doing nearly the same work as the tiger, but with much less energy, just tiny at the right place and at the right time. am I correct in saying that this is a very interesting hallmark of life? You use a lot of information in order to save energy. Every time that you go to pick mushrooms with your kids, if you know how to do that, then you use the book or the wisdom you gained from your parents. Think about millions of our ancestors who perished in agony, vomiting, and with diarrhea. Don't eat that red mushroom. Okay, so we actually survive by our ancestors died instead of us, but they gave us the information in order to survive more. So I can give more examples like that. So what is evolution doing? This has to do also with Yakir's measurement. Let me talk about weak measurement. Let me talk about signal and noise. So I'm making many transparent cards. Each of them has signal and noise. Why is it signal and why is it noise? The signal is always at the center. The noise is at different places, okay? So I have many transparent cards like this. Now I superpose them and I see that the signal is overcoming the noise. That's Schrödinger's famous equation. So you can see that evolution, when you have organisms which multiply a lot, then even tiny differences, which almost give you no advantage. Think about these mutations. Once this tribe of rabbits is in a place which is covered with snow, then those slightly brighter rabbits, their chance of surviving is slim, right? Because you could be slightly brighter rabbit, but then you would survive for many years and find a mate, and you could be a dark one, but the wolf has been busy at that day and the fox was sick, and then you survive. But at large numbers, the law of large numbers apply, and after a while, provided that you have a large number, then the very small signal can be multiplied with noise. This is how antenna work and so on. So this is information, and the next and last term that I want to introduce is complexity. So thermodynamics tells us what's the difference between order and actually mathematics tells us what's the difference between order and disorder, and thermodynamics build upon it. But what I want to show is that life is neither ordered nor disordered, but there is something very subtle in it. In order to do that, I want to make some measures of orderliness. So you see here 4 sequences of digits. So you would agree with me that sequence A is highly ordered. I am using 2 criteria by the late Lila Gatlin, who was a great biologist. What makes something ordered? Divergence from equiprobability. You have the same probability to find one digit rather than the other. So you see that the divergence is maximal at A and minimal at, say, C. Divergence from independence, given that you know certain digits. Can you now say, is the likelihood for the other digit to be something depends on that? And you can see that A is maximal while C is completely independent. And this is Gregory Chaitin's criterion. Can you compress it into any shorter algorithm? So you can see that A can be easily compressed. B cannot be compressed. Actually, the shortest algorithm of B is B itself. C actually is interesting, is something in the middle. What about D? So I was fooling you. D is just the post-decimal part of phi, and actually it's not random. But there is something very interesting in D. It is not ordered, not disordered. It is complex. Complexity is something that looks disordered, but every part of it is in place. And I argue that this is something very unique to life. Life sometimes looks disordered, but it has an algorithm, which makes it so unique. And this we owe to Charlie Bennett, who said, you know, that I've read many papers in my life. The rudest paper I ever read was published in the Journal of Theoretical Biology by a physicist named Hubert Yockey. And then he used some very derogatory words about a certain author. He compared him to Gulliver to Pooh Bah and so on and so on. The paper was mine. And that was I was a student, and a paper in the Journal of Theoretical Biology, 5 pages, which showed that my paper should never have been accepted. That was a major embarrassment, but he was right. He said Elitzur is confusing between order and complexity, and this is something that he didn't know, but Charlie Bennett has shown. Charles Bennett said the following: there is a difference between order and disorder in the sense that the ordered sequence can be easily compressed, and the disordered sequence cannot be compressed. Actually, it is the sequence itself. But there is something common to both of them, that you need very little calculation to do that. When you are reproducing a completely disordered sequence, you just type it. So it is, again, it doesn't take a lot of computation. Complexity differs from both order and disorder in that you need a lot of computation, either to compress it or to derive it again. So we are now moving from mathematics to physics. And now here is where biology can earn something. I would be very happy to find a diamond when I take a walk outside in the countryside. This is highly ordered and will make me very rich. I will be indifferent if I find just a rock. It's not ordered, many elements and just mixed together. But if I find an onion, it is not ordered and not disordered. It is something very unique. It looks disordered, but when I look at its detailed structure, I see many repetitions. All the cells are very similar. And here is something amazing. Every place that you put this onion, whether it is in South America, Australia, or Japan, not in Antarctica, it has information about the atmosphere, about the conditions on Earth in order to use them. So actually, the living organism is a kind of lawful Maxwell demon. It uses information, but it has earned it through natural selection. It is previous generations who have paid for that. So, this tree has information about G. Just those, yes, Ibrahim.
Can I ask a question?
Sure.
So I still don't understand the complexity. I mean, in terms of mathematical definitions, how do you define the complexity? In terms of order and disorder, I understand somehow, but the level of complexity, I don't have.
I would say that the third criterion, take the third criterion. Can you compress it? So you can compress easily something ordered. You can very little compress something disordered. You can compress something complex. It will cause you a lot of computation to do that. So that's complex. If the compression takes a lot of computation, and if, again, producing it from the compressed message take a lot of computation, this is complex. So you are now using time and energy.
You are saying that if I have a complete disorder, I cannot compress it. That means that the amount of energy I'm spending there is little. But if there is some pattern there, then I need to compress it. Then I have to spend a lot of energy. Then that will be another axis that I have to add to description. Okay.
So have I been completely ordered, I would be dead. I would be few crystals with all the energy stored in one bottle. Have I been completely disordered, I would also drop dead. Ashes to ashes, dust to dust. What is unique about us is that we are complex. What is unique to life, and this is something that I want to go into. So I argue that the satellites within the tree, within the plant cell, have information about G, for example, and I believe I can show that the more upward you go along the evolutionary tree, the information, the biological information becomes something similar to the laws of nature. We began with the Greeks with laws of nature which were very specific. They are good for a small range of phenomena. In time, they become more and more invariant, and they become more and more ubiquitous. You can see that actually this is what organisms are doing the higher you go on the evolutionary tree. Yeah, what's the relations between order and complexity? between information and complexity. I don't know what to say about this kind of work. There is a group, has been a group in this in Russia, Zotin and his group, and they showed the advantage of using thermodynamics to study biology in the following way. They took certain volumes of living tissue from various organisms. They measured the production of heat from each such an amount of living matter. And to this day, I don't know how reliable it is. They argued that the higher you go along the evolutionary tree, the greater the amount of heat produced by the body, if you factor for weight and size and so on. I mention it because if they are correct and this work is reproduced, not so far, I haven't found many reproductions, that would be a very strong indication how thermodynamics is a strong tool to study life, because these guys don't know much about, say, systematics, about zoology, about botany, but they can still tell you this organism has been through a very long evolution, while other organisms have remained the same for a long time. I say it's interesting. And now I want to close with the work I'm doing with Eliyahu Cohen, and which I find very promising. It's still a work in progress, so I'd love to hear your comments. We call it the ski lift pathway, and we say that what is nice about it is that it is unique thermodynamically, even surprising, but I believe it is ubiquitous. You know, sometimes when you fall in love with your own model, then everywhere you look, you think that you see confirmation to that, which should be sometimes worry you, but sometimes it works. And this is the case why I like very much this model. So I'm going to begin with a simple question. Mathematically, we understand what is the difference, if I manage to explain it, what is the difference between ordered, disordered, and complex, right? So ordered is something that can be easily compressed into a short algorithm without much computation. Disorder is something that you can't compress, you don't need much more computation to that. Complex is something that you can compress, but then it will take a lot of computation, a lot of energy and time, so this is physics. Now here's a question, and I confess I haven't found it in the literature. What happens if I want to change one state to another? So I know that if I have a system which is highly disordered and I want to make it ordered, I have to use a lot of energy. If I want to make it disordered, I don't need much energy, it will go by itself. What if I have a highly disordered state and I want to move it to another disordered state? Same disorder. Do I need energy? And how much energy do I need? And I must confess that I find it a bit surprising. So here it is. I have a maximum entropy that is very low order. And the transition from, so I know that the transition from disorder to order costs considerable energy, while the opposite is spontaneous. The question is, what is the cost of a horizontal passage? Low entropy to another low entropy. Yeah, Ibrahim is smiling, probably he's just picked the raisin from the cake much before me. Thank you, Ibrahim. I knew that. So I want to change from S max 1 to X max 2. And much to my surprise, I find that it is much more costly than going from X max 1 to S. I wish you were surprised. I was surprised by that. Nobody. Okay, Ibrahim is not surprised. Rahil is not surprised. What can I do? So going from minimal to maximal doesn't cost energy. Going from maximal to minimal costs energy. What about this? And you are not surprised. I'm surprised that you are not surprised, and I'm disappointed by that. What I want to show is that they are very costly, and the passage from one to the other, I hope that you will admit that it is a bit surprising, at least, Ibrahim, is this. So I have two ways of doing that. I can take the original one and now look ask how I can move it to the next, to the desired one. So I am taking the first digit and then I say, where should I put it? So you see, I have max 1 and max 2, and now I want to rearrange max 1 into max 2. Do you understand that I have to look for a place for the first digit? Where should I put the 1? And where should I put the 8? And so on. This, by Maxwell's demon, is going to take me a lot of time. I can do the other way, from the target to the origin. So this is the X max that I want. I begin with this, and now I'm looking for the digit, where to find the digit which I want to put. You understand that again, it's going to take me a lot of energy and a lot of time. What happens if I just go upwards? I wish you were at least a bit surprised, not a little. Okay, so you can give the talk instead of me. So it turns out that the best way to do that is just make it much more order than you want, then spoil the order towards the disorder. Ibrahim is not surprised. I'm surprised. I was surprised by that.
So the trick is that the second one is not actually, because it's defined disorder. So you are going to undefined disorder to a defined disorder. S max 2 is something defined, but it's still disorder, not order.
You say because it is precise. Yeah, that's another philosophical question. Some people, if Lev Weidman was here, I'm glad he's not, he would say that this is just a sort of, you know, people who studied in Russia always say second law of thermodynamics is not a real law. It is only subjective. I have showed by the 2 criteria of Gatlin that mathematically it is not so. This right here is unique. Although this is unique, there is another degree of uniqueness to that. Divergence from equiprobability, divergence from independence, compressibility. So it's different. If Lev was here, we would have a good argument. So I don't agree with him. There is an objective sense in which minimum entropy is minimum, not something subjective, whether I know it or not. Just let me tell you an anecdote. We all know who is the guy from Champagne, Urbana-Champaign, Nobel laureate.
Tony Leggett.
Tony Leggett. Once I even yelled at Tony Leggett. Tony Leggett said, I asked him about a cube of ice within hot tea. I showed him that. And he said, if I know the position of every molecule, then there is no entropy. And I yelled at him, and everybody who knows Tony Leggett, how humble and how sweet he is, he said, "Poof, I'm sorry, you're right." So I was privileged to get him by mistake. It is not that I have more information about it. Even when I have information, this is high entropy, this is low entropy, and this is high entropy again. So this is why we called it the ski lift model. Let me just, in order not to go into mathematics, take a visual example. You will agree with me that there is a lot of order here, maximal order, when the artist is beginning their work. With information, you would get this complex thing and this completely disordered thing at the end of the day in Leonardo's atelier, okay? So if Leonardo would want to change Mona Lisa into St. John, of course he wouldn't take every drop of color from Mona Lisa and change it into St. John. He would just say, bring me another canvas and another palette. So it is interesting that usually we take much higher order than we want and then spoil it. And I argue that this is what life is doing. So this is why we call it the ski lift. I would liken thermodynamic states to a mountain. So by Boltzmann's definition, there are very few ways to arrange these Logo cubes, right? Very few. So that will be the tip of the mountain. Many others to make it disordered. So easily things will go. So here the analogy helps me because gravity will help them spontaneously go down, whereas you will need energy in order to go uphill, okay? But then we have these complex things, which are neither ordered nor disordered. And now my question is, I know how to move from one minimal entropy to another. Shouldn't be a problem. How should I move from one disordered state to a complex one? How should I move from one disordered state to another precisely disordered state? or from one complex one to the other. And the surprise is, except for Ibrahim, is that you have to take what looks like a paradoxical path up this kind of zigzag. Look how important information is, because now when you have to do it, all you have to pick at the top of the mountain, the place where you want to degrade, the point there are very few points from which you can degrade. When I thought about it, so it is easier to go upwards and then go down rather than taking the short path. So Schrödinger was correct in the following sense, that it is not only that we feed on negative energy, we also produce reservoirs of negative entropy in order to whether in our bodies or in our environment. So let me show you a few examples. Yeah, this is very important concerning the mathematical side of it. In order to know whether a model is good or not, you have to know its limits. When is the ski lift worthless? It's not good. If you have few building blocks, you want to arrange them rather and then do something. If you have small between these two states. So a lot of work is being done to show where the ski lift is efficient, to show its limits. But the biological examples are very interesting. We begin as embryos much more disordered than how we eventually turn out. We begin completely symmetrical, spheric, all stem cells, and then something irreversible happens when we differentiate. You remember Einstein's frustration when he found out that he could have predicted the Big Bang just from his model, and he didn't see it until experimentalists told him that this is how it happens. I think that had I been brave enough many years, I would just by the ski lift predict that there is differentiation and redifferentiation, which is a complete revolution nowadays in biology. People thought that differentiation is irreversible. No, even in our body, in an old person's body, sometimes cells de-differentiate and then redifferentiate. The use for medicine is enormous once we understand that, how the body is doing that. But the body is using ski lift. Think about metamorphosis. Usually the caterpillar, when it turns out into a butterfly or an insect, it turns into a soup, which is highly disordered, many fewer chemicals, and then it rearranges them back, similar to the log cubes that I have described. Apoptosis is another example in which a programmed death of a cell is done by the cell being beautifully recycled. It doesn't disintegrate, but proteins are taken to one place, carbohydrates are taken to one place, and then are becoming ordered. This was Conrad Waddington, who had a similar idea. I wish he knew that thermodynamics and the mathematics of complexity supports his work. DNA replication, yeah, that's an example that people sometimes use to say your ski lift model is not correct. When DNA replicates, then it swims into a soup of nucleotides when you open these two strands, and each of them attracts the other. So this soup is completely disordered. That has been a problem to my model until I recalled what I said at the very beginning. Yeah, that soup is disordered chemically, but it is highly ordered energetically. There is a lot of heat there, and the molecules by themselves run. Remember how when I wanted to rearrange the log cubes, I had to look for the correct log cube. In this case, they come into me because there is a lot of energy there. So there is a high order in terms of energy. And this is the most devastating example, which I think about. I'll shut up not to say something political, but we know that we are wreaking havoc on our environment, on this globe, by our civilizations, right? We need very complex cities, and in order to do that, we destroy forests, fields, countryside, and so on. Actually, we are doing something much worse. Look at these cities. They are surrounded by huge order. Look at these monocultures of wheat, of corn. In order to, and as agriculture advances, they have to be more and more uniform. They have to be more and more, just the same in order for us to make the complexity. In order to do that, we are wreaking a much greater havoc on our biosphere than what we know. Schrödinger was correct, but in the sense that we can't only make do with the negative energy of the sun, we are creating huge reservoirs of negative energy around us. And then negative entropy around us, but then we are increasing the entropy, something to be worried about. Why I find this interesting, I'm working with some physicians and biologists. You know that the best way to understand the production of complexity and order is by infrared. When you create order, you create complexity, then there is a lot of infrared going on. By this model, you can see that you will have much more infrared when you create order and complexity. So this kind of U-curve that you can see sometimes, and I would love to have some collaboration with biologists, I think that we will be able to see this kind of scale of things going up and down in terms of infrared radiation that will show that every time that an organism in whatever process of life is creating complexity, it still have to go up and then down. For cancer research and other fields of biology, that could be very important. And of course, you know that Yakir has a different view of mind and life, and only recently he's thinking about a new way to apply this two-state vector formalism, not only for the idea of free choice. Yakir believes that every organism that actually he is going to propose, he thinks that he believes that he can propose a new definition of life, which shows that the more living matter is, it is because the more it is independent of the state vector coming from the future. I wish I could say more about it, but you have to leave it to Yakir. So I want to thank you very much for this opportunity, and I hope that this is the beginning of a collaboration on these issues for the next years. Again, thank you, Yakir. Thank you, guys of the Institute. Thank you very much.
Hey, thank you, Avi. Provocative. Anybody? Questions, comments?
Can you also define negative information? You define negative entropy. Is there a definition for negative information?
I was not prepared for this question. No, I honestly, thank you for the question. I don't know. Good question. Let me rather not answer your offhand. Why do I feel that you already have the answer? By your smile. Okay, we can talk about, but thank you for the question. Brian,
I have so many
family.
questions because, well, I was in.
tell me why you were not surprised. I worked years.
Well, I watched it from, when I was, by the way, that was a puzzle they gave it to us when I was kid. So you have some color papers on different chairs, and they ask us to go from one transformation to another
They
transformation.
did ask this very question.
Yeah, that question. That was the reason I was not surprised.
In
So
Iran,
the best way, the best strategy is that,
in our homeland,
yeah.
was in Iran.
Yeah.
So two Iranians had to meet here in Chapman. Okay, yeah, go ahead.
So that was the reason I was not surprised. I mean, the best strategy is not taking one and going there and going that way, but it's collecting all the same colors and then redistributing them. It's a kind of transformation. Assuming even if you put it in language of quantum mechanics, someone is asking you to take a vector in a block sphere to bring it to any arbitrary vectors that you want. What is the best strategy? Taking it to a non-one and then doing the transformation that you want. There's the best scenario that someone can do. There's a minimum number of interaction that you need, or minimum number of operation that you need to do that. So now I have a lot of questions about the physics behind. I mean, when it comes to, first of all, living animals, a machine, what is the definition of a machine? Being a living animal, right? Doing self-contained, so can operate himself, right, itself. Second is can grow, right? The third one is reproduce, okay? And that's the definition of the machine. When it comes to, let's say, the environment that we are living, the biological cells, of course, you're totally right. What's happening with the next generation is what is the minimum deficiencies in DNA? Because if we look at the DNA, you have billions of billions combinations. And it's not about the minimum energy, it's about minimum transformation of errors to the next generation. So when you talk about that, well, we are afraid of, mushrooms, well, if we taken the mushrooms, we died, right? So how this information is transformed to the next generation, and we are careful about that. I don't believe that exists there. You know what I mean? It's not really about the DNA, of course, has information, but what is important is the minimum deficiencies that should propagate. That's the first question that I have for you. The second one is that what would happen if I look at the entire of the world and the entire world is not expanding, but rather contracting? What will happen with the entropy? I will argue that entropy in this case will be going towards maximizing the entropy, minimizing the entropy.
To this I can answer because two great giants of physics already asked that. Hawking was interested about the master error of time. We have several errors of time: the cosmological, the thermodynamic, the gravitational, and so on and so on. Hawking once believed that if the universe what's the word? Not expand, contracts again, then entropy would go down. Daniel Laflamme showed him that it can't be. Suppose that I have a cup of coffee and it is being cooled. Suppose that at this very moment the universe stopped expanding and began contracting. It would be ridiculous to think that at that very moment my coffee would reabsorb heat. That convinced Hawking to realize that the thermodynamic error is independent and even more fundamental than the cosmological error, which is a surprise, something to think about. About your first question, I'll make it short. It will have to be, but here it is. We can't, there is no Lamarckian evolution. I can show it. I mean, if I work strongly with my muscles, it won't go into the DNA. And the reason, the thermodynamic reason is simple. The DNA is a tiny molecule. How could you get something going from the macroscopic precisely to the microscopic? Nature apparently cannot do that. I say apparently. So you have to have Darwinian evolution, which is crude, blind, cruel. You have to have millions of human beings, Homo erectus and all that, dying from eating the wrong mushrooms in order to leave those few, whether genetically or culturally, who eat the correct mushrooms. Nowadays, there is a new revolution that shows that even Lamarckian evolution sometimes can work with the aid of very small microorganisms that we get through our mothers and so on. This is a new revolution in physics. What I can say, and I should have said it in the talk, what is unique to life, this is nanotechnology. So you have a problem. If you build a big machine, it will be much stronger than the organism, but the amount of entropy production is great. If you build a molecular machine, very little entropy, even zero entropy, but then it's very small. Here is what's unique to life. Many, many engines like this. So the difference between me and the car is that there is one engine doing one work, a lot of entropy. Here you have zillions of engines working in an orchestrated way in order to do the same. So this is what is so unique to life, which nanotechnology is only now beginning to learn. So if you're asking about what is unique to life in terms of the microscopic and the macroscopic, is that life, just like nanotechnology, manages to have 2 feet on the 2 sides of the quantum classical realm. I should say, nowadays we have quantum biology. Until 20 years ago, if somebody said quantum biology, we would say that he's a charlatan. Life, we are too wet, too warm to have coherent effects. Now we know that very likely photosynthesis is utilizing quantum mechanical mechanisms, birds navigation, and so on. Roger Penrose believes that our mind is using quantum effects, which is what Yakir wants to show too. So this is a very vast issue on which I touched just a little. Yes, Jeff.
Just to follow up, and Ibrahim, maybe I didn't quite hear you, but consider, for example, protein conformations, right? If you look at the energy landscape, I mean, there's what, 400 trillion relative minima, only a couple of which are relevant for life, right? Most protein conformations are relevant. You seem to be saying that maybe I couldn't quite hear you correctly, but one question is, how does life find just those couple out of 400 trillion? But you're saying say it again, because I couldn't hear.
Is the amount of error that may propagate upon the times. That's it.
So
Those DNAs, they contains less errors.
Very little.
Yeah. I mean, you can go with many contributions and the distributions of them, and you look at the minimum energies of them, of course, that's the requirement, but only those survives that they produce less errors on the next generation. I mean, I was on exactly the same page as you, but I believe that is minimum energy, maximum entropy that is dictating everything. But then when it comes to the life, it's really the productions and reproducing and how that next generation will has less deficiencies.
your question is like that of Yakir. I better not answer immediately. Yeah, I have to think about it a lot. Thank you very much again.
Might be a question on Zoom.
Zoom.
Looks like someone has a hand on the Zoom screen there.
Oh, yeah.
Why, go ahead.
Oh,
Can we hear you?
Oh, my goodness. How are you doing?
Wait, it-
Hi,
Good.
hi, do you hear me?
We hear
yeah,
you.
Yeah, I can hear you.
Yeah. First of all, I would like to thank you for this very interesting, brilliant talk, which have caused many thoughts. Could you please show once more the slide with Gioconda and this analogy?
This analogy?
Because I have related question.
Who have the ski lift analogy?
Which analogy? This one?
No, I mean the painter and the
Yeah,
portrait.
sure.
Of,
I love
yeah.
it. Yeah. Go ahead.
Yeah.
Okay.
It's a.
So here you're in high order.
Can you show the result? Yes, with the one. Yes, the one with okay. So it's in my opinion, it's a brilliant illustration how nature could act, and well, we know that disorder is the state is maximal entropy, and the subject which has maximal entropy is black hole. So imagine this disorder is a black hole, and this is the result of some processes in the universe. Then, according to this analogy, it could be that something as beautiful as Gioconda portrait can also exist in the universe, like a job by cosmic painter or God or whatever. Could you comment or?
All I can say is that I'm stunned. The question is profound. The question is very profound. Now I can't comment on that. I have to think about it. So now it's 3 questions in one talk in which I have to think about Yakir, Ibrahim, and now you.
Gleb.
Gleb, yeah. So I have to think about it. And when we meet again, I hope I'll have an answer. Yeah. So thank you again for a very profound question.
Yeah, thank you a lot, and it was real. I enjoyed.
Thank you very much. My pleasure.
Okay, that's Gleb from Ukraine. Thank you, Gleb. All right, everybody, Yakir's going to talk at 4. If you thought that was exciting, you're
wait.
Not. Yes,
I'm just a warm up. I'm just a warm up. Here's the master.
And now for something completely different. Modified. Thank you.
Thank you. I mean,
Okay.
No.